Okay, good. So, so last time we quantized this theory. So let me just write down the theory again. Okay, so we quantized this theory, and so so let me also just write down its canonical momentum density, and then the Hamiltonian density would be half I squared. Okay, and the classical equation motion. Okay, and so we'll not repeat the quantization procedure, and we wrote down the most general solution at the quantum level. Can be written as the following. This factor is a convention, and then we have AK, UK plus AK. So from now on, I will suppress the hat. Okay, so I will suppress hat. You should always now view it as a quantum field, quantum operators, and the plus UK stop. Okay. And UK is the complete set of solution, which is given by exponential minus I omega t plus AX. Okay, so this is just the basis of solution. And so this is the most general. So this is the complete solution to the operator equation for this operator phi. And then you can also find its conjugate momentum density. So the pi, you can just take the derivative straightforward. I will not write it explicitly. Okay? And then we discussed that you can impose a canonical commutation relation, which is that the phi px phi px prime equal to pi px and pi px prime should be 0, and then phi px pi px prime then given by the delta function. Okay, so that's what we did at the end of last lecture, and then you can just plug it in, plug those expressions into here. Then you can find the commutation relations between those integration. So AK and AK dagger are integration constants of your operator equations. They're constant operators. Okay, and so when you plug them in, then you find the canonical. Then you find the commutation relation between AK and A dagger, and then you find that AK and AK prime equal to A dagger K and A dagger K prime is equal to 0, and AK prime dagger is equal to delta function in the wave space. Okay. Okay. So now this is. So now if you look at those expressions, so we essentially find the infinite number of harmonic oscillators. And each harmonic oscillator labeled by continuous by a set of continuous number k, and then the commutation relation is just like a continuum generation of standard a dagger equal to 1. Okay, and they're independent because of this delta function. And if k is not equal to k prime, and then you get 0 at the commute. Okay. So you can see the story a little bit sharper. That indeed we just get infinite number of harmonic oscillators. So these are just commutation relations. This still does not tell you we have a harmonic oscillator. To see harmonic oscillator, we actually need to calculate the Hamiltonian. Okay, so now let's try to calculate the Hamiltonian. So now we can try to calculate the Hamiltonian. Okay. And so this is just, you can just do it straightforwardly, just plug that in. Okay, just plug that expression in. Okay, we wrote above. And then you just plug in the expression for the phi and the pi, okay, into that equation. And then you just straightforward to calculate it. Okay? And I will not go through the details. It's a straightforward calculation. So then you find, maybe after some minutes, then you find the following answer. So now when you plug them in, then you find you can actually do the spatial integral, because you just have the plane wave. Okay, you can just do the spatial integral. And when you do the spatial integral, then that gives you a delta function, momentum space, etc. And then you can reduce everything into a single k integral. And then what you find is you get omega k, and then you find ak dagger, ak, and then plus, say, AK dagger. Okay? So let me see. Yeah, actually, I think 1/2. Okay, just get that. Okay, so this is the standard expression for harmonic oscillator now. Okay? Actually, it's exactly identical to you just sum. Integral is like sum, just sum over continuum harmonic oscillators, and each with frequency omega k, and each harmonic oscillator is labeled by this number k. Okay, and so we can do from the standard trick to write it actually as a commutator. So we can just write it as omega k, and then we just have this. So we combine these two terms together and introduce a commutator. Okay, you just have a dagger a, and then plus the commutator between them. Okay, let's get that. So in the standard story, this is equal to 1. Then you get the standard answer that you get omega a dagger a plus 1/2. Okay, but here, so we can again, let me just write one more step. So this is k omega k, ak dagger, ak, then plus E0. And now E0 is the sum of all the 0-point energy of all the harmonic oscillators. Okay, so 1/2 omega k. Except the tricky thing is the following. Okay, except now we have this commutator of AK with AK dagger. In the standard case, this is equal to 1. But in our case, Okay, in our case, when you set k prime equal to k, we get delta 0. Okay, so we get delta 0. So and then we get instead 2 pi cube delta 3 0. And remember, this 0 is in momentum space. Okay, and so this is in k space, not in the. We have two kinds of delta functions: the delta function in k space, delta function in coordinate space. So here I put the subscript k here, means that this is the delta function 0 in k space. Okay, and so this is a 0-point energy. Okay, so this 0-point energy is divergent, but we will comment on that a little bit later. Okay. Do you have any questions on this? Good. So remark. Let me just make a couple of remarks. First is that something interesting happened. So when you look at the expression for phi and the pi, both phi and the pi depend on time explicitly. Okay, so there's a time dependence here. And here we only integrate over spatial direction. Okay, we only integrate over spatial direction. So in terms of integration, we don't do anything with time. But what do you notice here? What do you notice there?
Drop the time dependence?
Yes, it's not saying we drop time dependence. Just time dependence disappeared. Do you know why?
I mean, the Hamiltonian doesn't like explicitly depend on time, right?
No, the Hamiltonian phi is time dependent, pi is time dependent. If you plug those expressions into here, certainly inside there is dependent on time explicitly. This guy is dependent on time explicitly. Yeah. But in the end, after you do the integration over spatial directions, then you find in the end the time dependence actually cancel during the calculation. Okay. So do you have a guess why somehow this should cancel? Yes?
Like energy conservation or something?
Yeah, exactly. So you have done in your P set that the time translation. So this system is time translation symmetric, and means that you should have means that the H, okay, is a conserved number. Okay, it's a conserved quantity, and so then indeed you see that this is independent of time. This is a conserved quantity. Okay, we see it explicitly. Okay, so there's no time dependence. Since H is a conserved quantity. So this integration is absolutely crucial, because if you don't do integration, the Hamiltonian density is not conserved. Okay, it's only the total Hamiltonian is conserved. Okay, so this is a comment. And the second, yeah, let me. So yeah, since I only have two comments, let me just call it 1 rather than call it 0. So the second comment is that then just repeat, we already said, you just QFT of phi. We see this QFT of phi reduces to essentially a system of a continuum of harmonic oscillators, okay, labeled by K, with frequency omega K. Okay, so recall this omega k is defined to be k squared plus m squared. Okay. Okay. So as we mentioned the last time, the fact that we actually see infinite number of harmonic oscillators is actually not surprising from the perspective that this field theory can be written as the continuum limit of a chain, say, of atoms connected by springs. Okay, so when you have a chain, we draw down a one-dimensional system. You can easily generalize to three-dimensional. Yeah, so you have those chains of atoms connected by spring, and they are just coupled oscillators, and then you can just diagonalize them, and each find the normal spectrum, and each of them is just a harmonic oscillator. And so when we find those solutions by doing Fourier transform, and essentially we are just diagonalize those interactions between those springs. Okay. And so that's why we get infinite harmonic oscillator. So from that kind of way to think about it, it's it's totally unsurprising we get the infinite number of harmonic oscillators. But it's not surprising. It is surprising if you think about it from the point of view of a field theory. Okay, so if you find when you quantize a field theory, and then you find in the end you get a bunch of harmonic oscillators. Okay, and before doing that, it's hard to. Before you actually carry out the quantization, it's actually hard to anticipate that if you don't have this intuition from this discrete system. Okay. Do you have any questions on this? Yes?
So when you say that there's an infinite amount of harmonic oscillators, are
Yeah.
you saying that there's an infinite amount at any given point in space, or that at each given point in like a continuum of location, there's one harmonic oscillator?
Yeah. That's a very good question. And it's at each point you have a harmonic oscillator. Yeah, at each point, essentially at each point you have a harmonic oscillator, and then they're connected in space. Yeah. Yes.
Is there any reason why we didn't compute the k integral in E0? I mean, you have a delta function in there. Why did you just write down?
Sorry, say it again.
So the integral
Yeah.
E0 equals. Why didn't you just?
Oh, this we cannot do this integral.
No, up there.
The 0 point there.
Oh, right. Yeah, we will talk about this a little bit later, because later we are going to elaborate on this a little bit later, because we are going to try to give interpretation of this. Yeah. Yes.
In homework 1, we found that A hat was time dependent. Is A hat not time dependent here? And is that why the Hamiltonian is not time dependent?
Yeah. A hat is a constant operator.
Okay.
Yeah, because A hat is the integration constant of your operating equation. Yeah. Yes.
Is there analog of coherent states for each harmonic oscillator in the QFT?
Oh, yeah. There's analog of coherent state. Yeah,
Can
indeed.
they tell you anything useful? Is there a nice physical interpretation?
Oh, yeah. You can. You will see. This question will become clearer when we talk a little bit about the Hilbert space. Yeah. Other questions? Okay, good. Now let's. Before we talk about the Hilbert space, we need to talk about two things. So here I have a dot. And the second thing, so Hamiltonian is an important quantity. So this is one of the conserved quantity. So there are other conserved quantities. So there are other conserved quantities. And one of them is the conserved quantity corresponding to spatial translation. Okay? So the spatial translation gives you conserved momentum. Okay? Momentum conservation. So So from spatial translation, then you get this conserved charge, Pi. Again, you should have done this in your homework to have the following form. T3x pi. Okay. So this is the loss charge for the conserved quantity associated with the spatial translation. Okay, and we interpret it as a space-time momentum. So this should be interpreted as space-time momentum. So this is, so here we have two momentum here. You don't confuse of them. So this pi is the canonical momentum conjugate to this canonical variable. Pi is the canonical momentum conjugate to this field variable phi. And this is the genuine physical space-time momentum. Okay, it's the momentum of your full system. Okay, of your full physical system. And again, we can just plug this in. Okay, we can just plug in the explicit expression of pi and the phi. We already know its time evolution. Okay, we already know their time evolution, and then we can plug them in. And then you find that the answer is given by, again, after some smaller number of minutes calculation. And then you find that the answer is given by this. In this case, there's no 0-point energy. You just have this expression. Okay. And furthermore, you also have a Lorentz transformation, Lorentz symmetry. And then that will lead to, say, the conserved charge associated with Lorentz transformation. And again, you can find it explicitly. Okay? And so in your P set 2, you will find the expression of this mu, say, in terms of phi and the pi. And then you can again express this guy in terms of A and A dagger. But I didn't have the guts to assign it as the part of the P set. So I used it as a bonus problem because that calculation involves a little bit actual calculation. Yeah, it involves a little bit slightly more tedious calculation. So I used it as a bonus problem for those people who like to have some more fun. Yeah. Anyway. So this you can will see it in your P sets. Okay. Good. So and then again, Pi you see it explicitly that this is time independent. Okay. Is time independent. Good. And then the next thing is let's talk about this 0-point energy. So this 0-point energy, we can write it as the following. So we can, so this is a constant. So we can take it outside of this K integral. Okay, this does not depend on K because the, So this is just 2 pi cube delta 3, 0. So this is, remember, this is a K space delta function. And then you have D3K. Okay, so that's the expression we get. So now let's try to understand what's the meaning of this term. Okay, let's try to understand the meaning of this term. To understand the meaning of that term, we need to do a little bit of mathematical trick. Okay, we need to do a little bit of mathematical trick. So remember, the definition of delta function, we have 2 pi cube delta 3k equal to the Fourier transform of exponential ikx. Okay, so this is the definition of the essentially the definition of the delta function. Okay. And now here we want to set k equal to 0. Okay, so let's set k equal to 0 here. And then we find that this 2 pi cube delta 0. So let's remember this again in the k space. And then we just set k equal to 0 here. And then what is this? If you set k equal to 0, you get what this? Yes?
The volume.
Yeah, that's right. You just get the volume of the full space. Okay? The volume of the full space. Let's just imagine you, in order to make sense of this quantity, you can put the whole universe in the big box. Imagine the whole universe is in the big box, and then this is the total volume. Okay. And then now since this is the volume, now we have very good interpretation of this quantity. And now we can write E0 as volume times epsilon 0. And then this quantity, epsilon 0, then have the interpretation of the energy density. Okay, so now this is energy density. Okay? So this energy density, we can write it in one more step. So continue to here. So we can write it one more step. Plug in the explicit value of omega k. So this is the just 1/2. Sorry, I forgot 2 pi. 2 dk, and then you have omega k squared. Yeah, so that's what you get. Okay. So how do you like this integral?
So just a question to go back here. So
Yeah.
Wouldn't it be equivalent if you just left the delta function inside of your integral and just say that it's one for your entire, like for all k? So why are those two pictures equivalent? Because in that picture you don't get the volume.
Sorry, say it again. What's two picture?
If you didn't pull out your delta function from your integral,
Yeah.
you just did it, wouldn't that delta function is one for all k?
No, because this is just a constant, right? Just when you have an integral, you have a constant, you can always pull it out. Because that delta 0 does not depend on k anymore. Yeah. Good. So how do you like this integral? Can you do it?
No, it's divergence.
Good. so it's fruitless to do this integral because this is divergent. And there's very good reason for this divergence physically. So this is just energy density. So essentially, this is the energy per unit volume. Okay? Say in some unit volume. So let's imagine you have a unit volume here. Remember this. Remember we said before, this is corresponding to you take a discrete system with some lattice spacing A, and then you take the lattice, and each lattice point you have a harmonic oscillator, and then you take lattice spacing A go to 0. So that means for any unit volume, when you take A goes to 0, you have infinite number of oscillators inside. Okay? So essentially, when you have the lattice of oscillators at each point. Yeah. Anyway, I will not try to draw it. And then when you take A to 0, you have any volume unit, you will have the number of oscillators go to infinity, and that's where this divergence comes from. Okay, it just comes from, in field theory, you have a continuum degree of freedom. So at each point you have a degree of freedom, and within any volume, then you definitely have infinite number of degrees of freedom. Okay, so this just from continuum of degrees of freedom. So this is the first time you see a divergent quantity in quantum field theory, but you will soon find that this is you find that this is the normal. Okay, it will be a fact of life. Just you will see divergence very commonly. Okay, and so because you have continuum of degrees of freedom. So the whole thing about quantum field theory is to find a way to deal with those divergences. Okay, and one of the key difference between quantum field theory and just finite quantum mechanics or finite number degrees of freedom is because of those divergences. And the big part of quantum field theory is to understand how to treat those divergences. And they actually don't affect your physics, and but you do have to develop sometimes sophisticated tricks to treat them. Okay. Good. And this infinite answer is also closely connected to a very famous problem you may have heard. It's called the cosmological constant problem. Because this tells you that any quantum field theory have an infinite, say, 0-point energy. And so you may say, okay, so also, in physics, whenever we see something infinite, there's one thing you always do to treat it. Can you guess what is the thing you always do when you see infinities? Yes?
Just like subtract infinity.
Yeah, that's one idea. That's one idea. But to subtract infinity is very hard. You know, in your calculus class, when you subtract infinity to infinity, you can get infinity, right? So you have to be very careful. Yes?
Just ignore the term.
That's another very good idea. Indeed, that's what we often do. Yes? That's also indeed what often. But to do all those things, you have to do one thing first. Yes?
Like approximately, it's like 1 over the Planck constant.
Yeah, it's also very close. You need to do. Yeah, exactly. You need to find a way to make it finite first, and then you can subtract it, and then you can. Yeah, just like when you sum 1 plus 1/2 plus 1/3, etc. You get an infinite series, but if you want to estimate it, yeah, you get divergence, but you always try to cut it off the series and then approximate by finite answer. And here is the similar. Okay, so here we always put some momentum cut off. Okay, say imagine the momentum is smaller than some momentum, say some value lambda, and lambda corresponding to maybe to the scale which this quantum field theory no longer apply. Because nobody told you that this quantum field theory should apply at all length scale. Because, for example, in this lattice model, this scale would be 1 over the lattice spacing. Okay, would be 1 over the lattice spacing. Anyway, so once you cut it off, still you get a pretty big number. And you cannot ignore it because this is a physical 0-point energy. In principle, you can measure it. Okay? But in real life, we don't see it. So we have quantum fields flying around all the time, okay, but we don't see this big vacuum energy. So this is called the cosmological constant problem. Okay. Actually, there was just a colloquium last week about this cosmological, related to this cosmological constant problem. Good, any questions? Okay, now we can talk about Hilbert space. So as a harmonic oscillator, so we can first define the vacuum state. So now what we will do is indeed, in quantum field theory itself, we can just ignore this E0, okay? From now on, we will just ignore this E0. Because this is just give you overall, just give you constant, which does not do anything. Okay, it's like the potential energy in E and M. Just like the unit. Just like the anyway. So from now on, we ignore this term. Okay. So often I will just write Hamiltonian. I just write this term. But later we will actually see examples. Okay, later we will see examples. Actually, this E0 can actually have physical implications. Okay, but just for our current purpose, we ignore it. Okay. So now the lowest energy state, then it's clear from here, because this is just a constant. So the lowest energy state, ground state, which is we often call the vacuum state, means there's nothing there, is given by AK 0 equal to 0, defined to be for any k. Okay, so the ground state satisfy, which I denote by 0, then satisfy annihilated by this AK. And then the general state, okay, you can just, so general states have the following form. Say I can write NK1. So the K1 oscillator excited n times, NK2, the K2 oscillator excited NK2 times, etc. Okay, which is given by, which is proportional to, say, AK1 dagger to the power NK1, AK2 dagger, NK2, etc. acting on 0. Okay, just like we have a large number of harmonic oscillators. Okay, yeah. Questions on this? Yes?
How do you know there exists some state that's annihilated by every single annihilation operator?
Or you postulate. Yeah, you postulate, but you can actually write it down. You can actually write down its wave function. Just as in the standard harmonic oscillator case, you can, starting from a dagger, say annihilated by A, you can start from this equation to write down its wave function. And here you can write down the wave function for the vacuum states too, in terms of phi.
Okay.
Yeah. Yes?
In the notation for detector, it looks like we have a countable number of frequencies. Is that?
You mean here?
Yes.
Yeah, here I'm just saying, depends on which K are excited. Yeah, that's a very good question. I will comment on related issues very soon. But here I'm just write down some states. Yeah. Yeah, I excite K1, K2. Yeah, as I want. I'm not saying that this is the. Yeah, you can have as many as you want. Yeah.
Yeah, but if you use that notation, it's still.
That's right. It's true. Yeah. When I write it, when I write this way, it implies I only excite countable number of them. Yeah. Right. But in principle, yeah, we will soon touch a point which is related to your question. Yeah. Other questions? Okay, good. And so, for example, the simplest excited state would be just excite one of them. Okay, so let me denote this by K. Okay. And then the next simplest one, you just excite two of them. So this K1 and K2 can be the same. Okay, if this K1 K2 are the same, and then you just like the square. Okay. And here also I will not be very careful about the normalization. Okay. And now we ask, what are the physical interpretations of those states? Okay, so now let's ask, what are the physical interpretations? Okay. So for this purpose, we can just look at their quantum numbers, okay, under, say, the Hamiltonian and under the space-time momentum. Okay. So for example, H0. So if you act on H on 0, then of course you get 0, assuming we throw E0 away. Okay. Say ignore E0 so far. Okay. And then so for the ground state and the Pi acting on 0, of course it's 0. So you can see it just because this have AK here. And so E also, when we throw this away, you have this. Yeah. And now let's look at the excited states. So now look at this state. So H acting on K. So this answer is obvious because all different oscillators, they are independent of each other. And this just gives you omega K. Okay, we can just use our result for harmonic oscillator. Okay? And now you can look at the momentum. So this is a space-time momentum operator acting on here. And then it has Ki. Okay, if you look at this expression. Okay, when you do the act this on that, okay, you act this on that, and when you can just use the standard trick when you do the commutator, and then the particular K for this is chosen, and then the eigenvalue will be just given by that particular Ki. Okay, so there's one step of calculation there, and you should do it yourself. Okay, 1 minute calculation. Okay. There's a delta function you will be generated, and then that will get rid of that integral, and then you'll pick up this Ki. So now this equation has an obvious physical interpretation. So that means that this state K has space-time momentum. So now I write down a four momentum omega K and K. Okay. So this is exactly the momentum of a relativistic particle on shell. Okay. So this is the of a relativistic. So this is a momentum of a relativistic particle. Because omega K is equal to K squared plus M squared of mass M. Okay? Yeah, so this means that the P squared. So this is 4 vector square is equal to M. Yeah, so this satisfies the P squared equal to minus M squared. Okay? So we can just, so it's very natural just to interpret this as a particle of mass M. Okay, because yeah, you can just interpret it as a particle of mass M. Good. So now let's look at this one. So again, the calculation is very simple. So you find for that one, so you find for that one, for K1, K2, you find the energy, energy just defined. Again, you find that this is the energy eigenstate of the H. Okay, it's the eigenstate of H with energy eigenvalue, omega K1 plus omega K2. Okay, and it's a momentum eigenstate of Pi with eigenvalue given by K1 plus K2. Okay? So Ek are eigenvalues of H and P. Okay?
Question?
Yeah.
Yeah, so could that mask be 0?
So here, so this mass is not 0, right? Because omega k is defined to be this. That's defined by my theory, defined by my Lagrangian. Yeah, defined by my Lagrangian. So this is the parameter of your action. Yeah. Yes.
So we have a discrete energy spectrum, but like, does it happen the same way, like where the spacing gets smaller as you go to higher and higher energies, or?
Yeah, for here it's uniform. Here, just for each k, it's uniform. But of course, when you add them together, you get something very complicated. Yeah. But for each k, just uniform. So the most natural way to interpret this is just you have two particles. Of momentum of 4 momenta, omega k1, and omega k2. Okay? And similarly, you can do this for any state like this. Okay? They are all eigenvectors of H and P. So nk1, nk2, you catch it, etc. So this corresponding to nk1 particles of momentum. They're all on shell, okay? On shell particle of momentum k1. And nk2 has nk2 particles of momentum k2. Okay? So this tells you one thing. Okay, so now let me just make some remarks. Okay. Any questions on this before I make my remarks? Good. So the first point is that now you can see this can describe any number of particles. So mathematically, in our description, they are harmonic oscillators. But each excitation of the harmonic oscillators from the space-time point of view corresponding to a particle. Okay, so this is the beautiful thing of this theory. And then, because of the commutation relation, AK1 dagger, AK2 dagger equal to 0 for any K1, K2. So you have full symmetry. So when you construct the state, you can just commute them as you want. Okay, so that means they're full symmetry. In commuting all these different particles. In the general state, so this tells us these are bosons. Okay, these are bosons. Okay. And 2 is that all particles have positive energy. Okay, so even though that E square equal to K square plus m squared. This equation have two solutions, plus minus omega k. But when you look at physical state, when you look at your state and look at the eigenvalue of state, so all particles have physical energies. Okay, so you don't have this negative energy problem associated with taking the square root. Okay. Also, you have total energy of a state is equal to sum of energies of all the particles. So this tells you there's no interactions between them. Because if you have potential energies between particles, and then that will change their energy. When you put the two particles together, will no longer be the same of the sum of the individual energy for each particle. And so that tells you there's no interactions. So this is a theory of free particles. Okay. And this is a good starting point. At least now we have particles, okay? Questions on this? Yes?
So, with AK1, let's say, and you have a particle with momentum K1 now.
Yeah.
Is there a way to change this particle's momentum, or if you apply again, you, like in this picture, it's like you have another particle with momentum K1?
No, there's no way to change the momentum of a particle.
Okay.
So once you created that particle, it just goes straight. Yeah, it just it does not change anymore. Momentum, yeah, for that particle is conserved.
Is there, if you wanted to create a theory where you can change the momentum, is there a way, or is it just?
Yeah, there's a way. So after dealing with this free theory, and then we will consider the next simplest theory, and then that will introduce interactions.
I see.
And when you have interactions, then the particle momentum can change. Yeah. Yes.
So the things we're calling particles are like localized in momentum space, but not at all in position space.
Good. Yeah, these are the momentum. Yeah, it's like the plane wave in the non-relativistic. Yeah.
And if you were to like try to localize it in position space, like a Gaussian wave packet or something kind of like that, would you still be able to commute things? And
Yeah. So the commute things don't change because everything is built by AK, and they always commute, and so that won't change. But indeed, we will talk about the wave packet to localize in space. Yeah. Other questions? Okay, good. So the last, we will talk a little bit about the technical point. Is that so far we haven't talked about the normalization of such a state. Okay, so now let's look at the normalization of a state. So let's just look at this state. Okay, this single particle state. Let's look at this normalization. So let's look at K with K prime. Okay. So now if you take the overlap of this with the K prime, and then you can reduce this to the commutator of AK and AK prime, AK dagger and AK prime. So you will get just this. So again, this is a 5-second calculation. So you find this. Okay, if you do the overlap. But you already did in your P set. Okay, this thing is actually not a Lorentz invariant. Okay, this is not a good thing. This is not a good object under Lorentz transformations. Okay, but when we construct state, we would like to have our state to have good properties on the Lorentz transformation. So instead, so we will choose a slightly different normalization. Okay. So instead of this state, so we will define the following states. I will define a k, now without the vector, okay, to be the square root 2 omega k, and this k, okay. And so this is the 2 square root k, ak dagger, acting on 0. And now, if you compute the overlap with this k and k prime, so now you have square root k, square root omega k for one of them, and then you have square root k for two of them, and then you have 2 omega k, and then you have 2 pi cube delta 3 k minus prime. Okay? So now you recognize this object from your P set. The omega k multiply this guy actually have good Lorentz transformation properties. Okay? So this guy actually transform nicely. Okay? On the Lorentz transformations. So this will be the normalization we will use from now on. Okay? So these states have very, so indeed you can show, okay, so that will be, I think, in your P set 3. You should look forward to it. So you can show, if you act a Lorentz transformation, so lambda is a Lorentz transformation, and U lambda is the quantum operator to generate that Lorentz transformation on such a state k, and then you just get lambda k. And lambda k is the Lorentz transformation acting on that k. Okay, it's the Lorentz transformed k. Okay, and but yeah, you should see your maybe P set 3. Okay, so if I remember it. Good. Any questions on this? Yes? Yes?
So I'm not sure in this case here why we assume that omega k is the same for both k and k prime.
Oh, because you have a delta function here?
Okay.
Yeah, because omega k only depend on k, only depend on the spatial part. Other questions? Yes?
Yeah, so that inner product on the k prime, you said that's not Lorentz invariant. Is that just if you're like boosting one of the states?
No, just this guy, when you, it's not about whether it's Lorentz invariant, it's not Lorentz covariant. Just when you transform it, just this object, when you transform it, it's very awkward. Does not have very, you can transform it, you can write down a transformation for this object. It just does not transform nicely. Then that means if this does not transform nicely, it means each of them don't transform nicely. And then just not convenient. So this one have the property is that when I act U on this thing, and then actually you can just directly corresponding to the state with Lorentz Lorentz transformed momentum. Yeah, and then it's very easy. And this property does not apply to this one. It does not apply to this K. Yeah. Okay, good. So you can also talk about a wave packet. Okay, so this is the a plane wave. So this is like a plane wave. This is the momentum eigenstate. So we can also consider general. Say general single particle state will have the following form. So we have the following form. We can write it as psi, just as a superposition of this k. Again, you only need to integrate over spatial momentum, because only the spatial momentum are independent. And then some arbitrary function of k, and then on this k. Okay, so any single particle state, you should be able to write this way. Okay? So in particular, by choosing appropriate fk, you can construct a local wave packet. Okay? So you can, so choose k, you can choose fk to construct a localized wave packet in space, okay? So again, we will have some exercise like this in your P set 3. And also, earlier you could have objected when I call this to be a two-particle state, because each is a plane wave. So essentially, they're not localized. They cover all space, okay? And in one sense, they correspond to two particles. So now you can solve this problem, say, by constructing, say, using, say, dk1, 2 pi cube, dk2. So by choosing appropriate function k1, k2, this k1, k2, you can construct two widely separated wave packets, okay? Widely separated. Again, it's in space. So you can really talk about, so these are the genuine two-particle states, okay? And so that confirms actually this should be interpreted, yeah, as the plane wave version of the two-particle states, okay? Good. Any questions? Yes.
So now that we don't have the position operator like we did before, what's the conjugate, I guess, operator to our momentum operator? Or is there...
Good, good. That's a very good question. Indeed, there will be a problem in your P set 3 which asks you to show there's no eigenstate of there's no perfectly local. Yeah. So in non-relativistic quantum mechanics, you have this state. You have this wave function, say, we can localize at the point. But there's no analog of such kind of state in the relativistic case, precisely because there's no position operator anymore. Yeah, yeah. So you will explore this a little bit more later yourself. Yeah, yeah. Just with this formalism, you can explore all these questions yourself. That's the key. Actually, you already have the power to do that. Yeah. So now let's say a little bit more on the structure of the Hilbert space. So here, the structure of the Hilbert space is a little bit special because there's no interaction. So you can just separate it into, so the full Hilbert space, which I write as H, script H. Then you can separate it into the vacuum state. And then you have the one particle Hilbert space. And then you have the two particle Hilbert space. They don't have anything to do with each other because there's no interaction, okay? Okay. So in principle, you can have infinite number of them, okay? You can have infinite number of them. So if you restrict to always a finite number of particles, okay? So the set of states, so this is one particle. This is two particles, etc. So that's of states with a finite number of particles. Okay, it's called the Fock space. Okay, in the Fock space, we only have state of finite number of particles. Okay, but can have arbitrary number of them. Okay, as large as you want, 10 billion, 100 billion, but will be finite. Okay. So finally, those k, either this k or this k, they are just plane wave normalized, okay, because they're normalized by delta function. So strictly speaking, they are not normalizable states, okay? And so strictly speaking, they are not in the physical Hilbert space, okay? So strictly speaking, k, okay, or any those states of k, or k1, k2, are not normalizable. They are only plane wave normalizable. So just as say psi is equal to exponential ikx in non-relativistic quantum mechanics are not normalizable. Okay, are not normalizable. So they are convenient for various mathematical operations, but they don't correspond to genuine physical states. Okay, so not genuine physical states. So physical state, we have to consider, for example, this kind of state, and then you choose Fk, so that is normalizable. Okay. So if we take this, and then so with psi given by that, then the normalization of psi, you can calculate it, and then this is given by, so you can easily guess the answer. So when you do the overlap, etc., you find this given by the modulus of Fk squared. Okay? So if you do the calculation to calculate the norm of that state, you find it given by that. And then we can choose this to be finite, and then this will be then psi will be a normalizable state. Okay? So for this reason, sometimes, we don't do it very often, sometimes, can choose just a basis of fx, say, of fi, okay? So I run some number. And then this alpha, then you can define alpha I okay, and then this will provide, then alpha y will provide basis of the single particle normalizable state. Okay, a single particle state. So here is a fun fact related to the earlier question was asked. So naively, here you have, if you look at the K, so K form a basis. Okay, let's again just look at the single particle state. So naively, this K form a continuum, uncountable continuum of basis of states. Okay, uncountable continuum. But once you impose this normalizable condition, means you need to choose the normalizable F, and then you can show the basis of this normalizable F actually is countable. So in the end, the Hilbert space, the one-dimensional, the one-particle Hilbert space is actually generated by countable basis. Okay, just like in your ordinary quantum mechanics. Okay, it's actually rather than uncountable basis like in K. Once you restrict normalizability, so this is a fun mathematical fact. Okay. Good. Questions on this? Okay, so it's the last few minutes. We talk about conserved charges. Okay. Quantum rho of lossless charges. So classically, we say if action is invariant, if the action is invariant under some symmetry, some transformation, some continuous transformation, say of the infinitesimal form. Okay. Okay, so the alpha are the infinitesimal parameters. So the alpha label different transformations and A label different fields. Okay, alpha label different transformations. And then you will get the conserved current, J mu, labeled by this alpha. So alpha label different for each. So alpha label different symmetries for each symmetry, and then you have a conserved current, okay, which is satisfied the J mu alpha equal to 0. Okay. So the alpha equal to 1, 2, etc. label different symmetries. Okay. And then you can write down your lossless current. So we derive a general formula for the lossless current is given by the form, say partial L, partial mu phi A, and then FA alpha. So this is essentially the same as before. Essentially, I just add the index alpha. Now to label, you can have more than one symmetries. Okay, and then minus K mu alpha. So K mu alpha is the derivative, total derivative. Suppose delta L is given by epsilon alpha partial mu K mu alpha. Okay, so the K mu alpha is the total derivative corresponding to that corresponding to that transformation. Okay, and then the Q alpha then will be the conserved charge for that current. Okay, the zeroth component. Okay, so this is a classical story. Now I'm using a little bit more general notation for each alpha. So now the key thing. So now the key thing is that at the quantum level, so at the quantum level, first, as we already seen in the case of the Hamiltonian and the momentum operator, so Q alpha is time independent. It's a constant operator. Okay, so so this is to reflect that this is conserved. Okay. And also another important property of Q is that when you act Q alpha on your field, if you look at the commutator between this Q alpha on your field, it actually generates such a transformation. Okay, so turns out yeah, so if I put a parameter here, epsilon alpha, yeah, so it doesn't matter for Q, say it's upstairs, downstairs, and then you get, okay? So you just generate that transformation for F, for phi, okay? So this can be shown explicitly, okay? So you can show this explicitly. We are running out of time now. So you can show explicitly just using this expression. Okay, so let me just quickly outline the way to do it. So if you say, so let's look at the zeroth component of this J. Okay, so the zeroth component of the J just equal to partial L, partial 0 phi A, and F A alpha. Okay. So let's consider the yeah, I think today we will not have to finish. Anyway, yeah, let's just leave this to next time. Yeah, let me just say that at the quantum level, this will generate the infinitesimal transformation, and then you can also exponentiate this Q. Okay, you can introduce, say, exponential I lambda Q. So if Q is the conserved charge, and then you can exponentiate Q like this, and then this operator then generate, when it acts on phi, then generate finite transformations. Okay. So this takes you to phi A prime. Okay, the finite transformations. Anyway, so in your P set for P set 2, you will actually check yourself a couple of simple examples, and you will see this works. And in the next lecture, we will give you a simple derivation to show this actually works. Okay, it works in general.